Okay, so if I want to go from the name of a chemical to its formula, what's the first thing I need to decide?
Ionic or molecular?
I need to decide whether it's ionic or molecular. All right, what are some ways that I can tell the difference? If there's prefixes in the name, it's what?
Molecular.
It's molecular. Okay, so there's a dead giveaway. If it's got prefixes in it, it's molecular. And those are really easy to do because the prefixes tell me exactly what numbers to put on everything. Like, for example, number 53 here. Okay, phosphorus pentabromide. All right, so all I have to do is write out the symbols. Okay, the symbol for phosphorus is P. Since there's no prefix, there's only one. Okay, and bromine, Br. Right, and how many bromines are there?
5.
5. Penta means 5, right? And I'm done. I don't have to worry about dropping and swapping. I don't have to worry about charges or anything like that. Molecular ones, I just go with the prefixes.
Roman numerals are ionic.
Okay, if it's got Roman numerals, it's definitely ionic, as we only use Roman numerals on,
Ionic compounds.
okay, ionic compounds, but also on certain metals, right? Okay, so if I see a Roman numeral, I know it's going to be an ionic compound, but every time, if there's a what in it, it's ionic.
Metal.
A metal. Okay, so if I'm looking at a metal, then I know that I'm looking at an ionic compound. Okay, so let's look at, let's say an easier ionic one first. Let's look at 43. That's a very basic ionic compound. Okay, I have lithium, right? And when I'm doing an ionic compound, I write the symbol for the metal and its charge, +1. And then I write the symbol for the non-metal and its charge. For oxygen, that's -2. And then I drop that and swap it. So the 2 goes over here with the lithium, drop the 1, swap it. We don't write 1s. Okay, so I've got the formula done. Okay, everybody with me there? A little bit trickier one could be something like manganese, number 47 here, manganese, Roman numeral 2, oxide. All right, so first thing I want to do is write the formula for the metal, because that's what we're supposed to do as our first step, manganese, and then its charge. How do I know that?
The Roman numerals.
The Roman numeral. Okay, Roman numeral says this is the manganese that is the 2+ charge because it could be 2 or 4. Okay, so this is the manganese with the 2+ charge, and then it's with oxygen, which is -2. Do those already add up to 0?
Yeah.
Then I don't even need to drop and swap because this is already good that way, M and O. Okay? Now, they can also get a little bit more complex if I have something like number 50, where I've got a multivalent metal, so a Roman numeral, and a what? Polyatomic ion. Because when I write the formula, I might need to use brackets. Okay. So, same rules. I write the formula for the metal, lead is Pb, okay, and its Roman numeral is 2, so this is the lead with the 2+ charge, not the 4+ charge, and it's with hydroxide, which is OH. Okay. Now what I'm noticing a little bit, like I was looking at your quizzes yesterday, and people are not checking their periodic tables. Okay, because on a few of the ones that were polyatomic, people were writing elements. Like if it was nitrate, they wrote N. Okay, that's nitride. Okay, if you're not sure, and at this point, let's say you're not sure, check your periodic table to make sure you're writing down the right stuff, because everything else on those quizzes were done right, like the drop and swap was done right with the wrong material. Okay? So the easy part, which is looking up the material off the periodic table, was the part that people did wrong, and that's kind of more out of overconfidence, okay, than it is out of ignorance, which, I mean, honestly, that's a better mistake to make. At least you know what you're doing, but that whole, overconfidence can come back and bite you. That's what happened, right? So make sure you're always checking. All right, so hydroxide is OH, all right, and it's a -1 charge. So when I drop and swap, the 1 will go here on lead. We don't write 1, so that's gone. And the 2 will go here. But I can't leave it that way because that means 1 O and 2 H's. I need it to say 2 OH's. That's what the brackets do. All right, is that ringing a bell for everybody? Okay. I would like you guys to do okay, the ones circled in red are the ones I would like you guys to do right now. I'll give you a few minutes and then we'll walk through those. Okay, let's have a look at these ones. So our first one, we've got Mercury 2 nitride. Ionic or molecular? Ionic. It's got a metal, it's got a Roman numeral, okay? So Mercury is Hg, and the Roman numeral is telling us that that's a 2+ charge, and it's with nitride, which is the element nitrogen, okay, not a polyatomic ion. And its charge is -3. So now all I have to do is drop and swap. So the 3 comes to the mercury, the 2 goes to the nitrogen, and I've got my formula, Hg3N2. Okay, don't be afraid to ask questions if you got them as we go here, guys. All right, number 52, I got selenium tetrafluoride. All right, so ionic or molecular? Molecular. They're both nonmetals. There's prefixes in the name. Okay, so Se for selenium. Since there's no prefix on that, there's only one. And then there's tetrafluoride, which is how many?
4.
For number 55, we got nickel 2 sulfate. Ionic or molecular?
Ionic.
Okay, so nickel, and the Roman numeral tells me this is the nickel that's 2+, is with sulfate. What's that? SO4. It's a polyatomic ion. Guys, if it doesn't end in "ide," it's definitely a polyatomic ion. So if it ends in "ate" or "ite," it's definitely in there. There are a few polyatomic ions that do end in "ide," and those ones you have to be mindful of, like hydroxide. Okay, but if it ends in "ite" or "ate," it's on that. It's in that box. That's where you need to look for it. Okay, so SO4. Okay, and SO4 is a -2 charge. Is this okay the way it's written?
No.
Yes.
Yes, absolutely it is, because 2 and 2 add up to 0. Do I need brackets?
No.
No. All right, number 56, silicon dioxide. All right, ionic or molecular? Molecular, it's got prefixes, they're both nonmetals. So Si, there's only one of it according to that formula. Dioxide, O2. Then for 57, we have lithium phosphate. Ionic or molecular? Ionic. All right, so lithium is a +1. Phosphate is what?
-3.
Sorry, what's the formula for phosphate?
PO4.
PO4. Okay, and it is a -3 charge, according to your table of polyatomic ions. So when I drop and swap, the 1 would go here, but we don't write 1, so I don't have to worry about that. The 3 will come down to the lithium, and I'll have Li3PO4. Okay. Something else I noticed, I can't remember if this class or my period 4 class, okay, is that people are leaving the numbers up top. Okay, the numbers don't stay up top, the numbers have to be down below. They're subscript. Okay, so make sure that they drop down, okay, when you're done. All right, for number 60, we got cadmium nitrate. Cadmium, CD? Yes. Okay, not one I use very often. CD, okay, it's a metal, and it's 2?
Yep.
And that's its only charge, right? Yeah. Okay. All right, because otherwise there'd be what? A Roman numeral, and there isn't. I just wanted to make sure I wrote it right. Okay, and then it's with nitrite, which is NO2. 2. And NO2 is a -1 charge. All right, so now for this one, what am I going to need to use? Brackets, because when I drop and swap, I'm going to get a 2 here. I don't want NO22, I want NO2, 2. Okay? Very, very different. Number 63, I got lead 2 sulfate. So this is again an ionic compound because we have a metal and a Roman numeral. Right? The Roman numeral tells me this is the 2+ lead. And it is with sulfate, which is SO4. It also has a -2 charge, so do I need to do anything else?
No.
Nope, that one's good the way we wrote it. All right, and our last one, calcium sulfide. Calcium's a metal, so I treat this like an ionic compound because it is, okay? And it's with sulfide, that's just sulfur, okay, which is -2, so that compound is also good, CaS. This is ringing a bell for people.
Yeah.
Now looking at this the other way. Okay, let's just do a couple of examples from here first. Let's look at, actually I think we did a couple of these already, didn't we?
Yeah.
I feel like we did. But we didn't get very far. So, let's have a look at 13 first, because it's tricky. Okay? 13, okay, if I'm going from formula to name, again, my first step is decide whether it's ionic or molecular. That's tricky with this one, because it appears to start with a non-metal. Except it doesn't, it starts with a what? With a polyatomic ion. In this case, NH4, which is ammonium. So this is an ionic compound, so I just write the names of everything as they appear, and I make the non-metal, in this case, a polyatomic ion, okay, as my second thing. Do I change the ending of a polyatomic ion?
No.
Nope. Okay, so this is ammonium nitrate. Okay. We need a molecular one here. How about 18, because that's molecular. How do I know it's molecular?
Because there's 2 non-metals.
2 nonmetals. Okay. So what does C stand for?
Carbon.
Do I need a prefix on that?
No.
No, I would if it was a 2, but I don't because it's a 1. All right, and what's the prefix for 1?
Monoxide.
Yeah. You can write monooxide, but we typically call this carbon monoxide. Right? That is the poisonous gas, okay, that can be associated with poor combustion. So, yeah, if you don't have really pure combustion, that gas can be produced, and it obviously makes you sleepy, and then bonds to your hemoglobin and makes it so that your body cannot transport oxygen. It can kill you. Okay. Now, it's actually why, I don't know if any of you have noticed this, but if you have a garage that is attached to your house, the door into your garage has a hinge that closes it automatically. Okay, that's building code because they wouldn't want carbon monoxide to get in the house because the door to the garage was left open and somebody's command start accidentally started their car, because it's happened. Okay, when command starts first came out, that wasn't code. Okay, and lots of people died of carbon monoxide poisoning because their door was open to their garage and their command start started their car with the door down. Okay, and you know, like you have your remote, right, and you bump it, you don't really notice it. Okay. Like the guy down the street from me, he bumps his alarm all the time and apparently never notices it. I can hear it clear as day, but apparently he's hard of hearing or plays his music really loud or something because his car horn's constantly beeping and nobody ever shuts it off. Okay, so it'd be really easy to miss if your car was, you know, just had a small car just idling in the garage, okay? And then your house would fill with carbon monoxide. All right, I want you guys to try the ones I circle here. So let's go with this one, this one, this one. there aren't any with Roman numerals. What's with Roman numerals? Oh, they're all down here. Okay, forget that I circled this one and this one. I need to go further down so I can get some that have Roman numerals. That one. Okay, I want the names for those circled compounds. Okay, so for number 17, I've got nitrogen and oxygen. Is that ionic or molecular? It's molecular. They're both nonmetals. So I'm going to name the first nonmetal exactly as it appears on the periodic table, nitrogen, but how many are there? 2. What do I need to put in front of it? Di, right. I've got to have a prefix because this is ionic. All right, so I've got dinitrogen trioxide. Okay, second nonmetal ends in I. Second nonmetal always ends in I that finishes a compound. All right, number 19. People will often look at this and go to their table of polyatomic ions and say, this is nitrite. Except it's not. Nitrite can only be part of what kind of compound? Ionic. This is by itself. So this is actually a molecular compound, and it would be called nitrogen dioxide. All right. Okay, the one below it, ionic or molecular? It's ionic. It's tricky, right? Because we all think hydrogen's a gas. That means it's not a metal. But in actual fact, hydrogen's a gas, yes, but it's also the most metallic thing there is. Okay? So if we have this, if hydrogen is listed first, it's behaving as a non-metal, or sorry, as a metal. As a metal. If it's listed second, it's behaving as a non-metal because it can do both. Right? But it is, in fact, very, very metallic. All right? So this will be hydrogen sulfide. Okay, now something that often comes up. I often have people when I give out kind of the final assignment on chemical reactions, and part of it is writing the reactions out in words, so basically doing a bunch of naming. I often find that people will like cheat, and they'll just Google a name. Here's the problem with it. I'll know if you Google the name of this, because it won't come up as hydrogen sulfide, even though that's its technical name. It'll come up as sulfuric acid. Okay? We haven't gone over naming acids, and we're not going to. Okay? That's for Chem 20, right? We don't do that here. So the point being that you need to, A, not cheat, and B, okay, learn how to name these for yourself, because you won't be able to Google it on the unit exam.
And she wrote this before we did it.
It's like I can tell the future, that's why I'm doing it. Okay?
Right.
It's not that I can tell the future, it's just that it's happened so many times in the past.
Unless I think so. I'm not saying that we would, but like at least we got a warning. Yeah.
All right, number 23. Okay, we've got K and N. So what does K stand for? Metal or non-metal?
Metal.
Metal. So this is ionic. So we'll have potassium nitride. Okay, and then for number 25, we've got magnesium and fluorine. Magnesium's a metal, so this is ionic, and it will just be magnesium fluoride. Okay, don't need any Roman numerals on any of these yet, because none of them have two charges, right? Okay, number 27, I've got aluminum, which is obviously a metal, with oxygen. So this is an ionic compound, so we have aluminum oxide. Okay. I often find that a common mistake is when there's numbers on both, ionic or molecular, people just desperately want to put prefixes on there. Okay? Remember, this is ionic, it doesn't need prefixes. It doesn't matter how many numbers. If it's got a metal in it, no prefixes. All right, and then for number 28, Pb is lead. Okay, so we've got lead, and it's with sulfur, so it'll be lead something sulfide, except that lead has more than one possible charge. So I need to figure out which one it is, so I can put what in this?
Roman numeral.
Okay, so sulfur is always a -2. there's only one sulfur, there's only one lead. That means this lead must be a 2+ charge. So this is lead 2 sulfide. Okay, I know there's lots of little nitpicky details that you have to remember, but you have to remember them. They're all important. Okay. All right, I am going to have you guys try a couple more of these, and then we're going to move on to solubility and polar nature of water. So, why do I have a square? I don't want a square. What's the square for? Weird. So weird. Where's the square from?
There's no
What?
from what I'm
I don't
thinking.
know where
It's
that's.
maybe tap.
I tried that. It won't go away.
Is there an
Tap on
edit
the-
bucket? No bucket, wow. It's just
There
not
we go.
really.
All right, it's gone. Okay, I would like you guys to try 5, 8, 10, 13, 11.
Oh. Wait a minute. It would be 9:20 in August.
All right, those 6. So have you tried those 6. Then we're gonna do 6 more that are the other way, and then we'll move on. Okay, so for number 5, okay, we've got phosphorus trichloride, which is a molecular compound, 1 phosphorus, 3 chlorines. Okay, for number 8, we got cobalt 2 nitride, so CO, it's a 2+ because the Roman numeral tells me that. Okay, the nitrogen's a -3, so I got CO3N2 as my formula for that one. For number 2, similar idea. I've got nickel. The Roman numeral tells me it's the 2+ nickel. It's with fluorine, which is a -1, so I'm going to have NiF2 for that one. For number 11, manganese 4 selenamide, or selenide, whichever way you want to say it. Okay, so manganese is Mn, and it's the 4+. Selenamide is a 2-, I believe.
Yeah.
Okay, so when we drop and swap, we're going to get 2 and 4, which we can reduce to
1 and 2.
1 and 2. Okay, so we can't forget to do that. That doesn't, I mean, it happens once in a while, but it is something we have to remember. And then oxygen difluoride, so molecular compound, 1 oxygen, 2 fluorines. And lastly, disilicon octachloride, so that's Si2Cl8. Do I reduce that one?
Yes.
Nope.
No.
Because it's molecular.
Oh, yeah.
Molecular, they tell me the numbers, I stick with the numbers. Okay. In ionic, it's the lowest common multiple because, okay, or lowest form, sorry. Okay, because it's about balancing charges. Okay, so they go together in the lowest form. Alrighty, then. Come on. Ooh, the hamster in my computer must be sleeping. Yes.
Oh, that's what I know. Oh,
I was just making sure.
Honestly, I thought of it.
All right, I want you to do those 6. Write the names for those. Okay, let's have a look at these ones. So our first one here, we've got N2Cl3, so that's molecular, right? We're going to have dinitrogen trichloride for that one, okay? Putting in our proper prefixes. And then for the second one, we've got iron and nitrogen, so that's ionic. Iron has more than one possible charge, so I will need a Roman numeral in that name. It'll be iron something nitride. Nitrogen's always -3, and there's only one of each of these, so this is the iron with the 3+ charge, so iron 3 nitride. All right, number 3, we've got calcium with sulfate, so this is another ionic compound. Right, I don't need any Roman numerals because calcium only has one possible charge, so we're just looking at calcium sulfate. And then for number 4, another ionic compound because beryllium is a metal. All right, we have beryllium bromide. No prefixes, no Roman numerals on that one. And then for number 7, I've got cobalt with nitrate, but cobalt is a multivalent metal, so it's going to need a Roman numeral. So nitrate is a -1, but there are 2 nitrates, okay? People often make a mistake here and they say 6, okay? There's only 2 nitrates here. There are 6 oxygen atoms, yes, okay? But there are only 2 nitrates, and it's the nitrate that has the -1 charge. So I've got 2 negatives that I've got to balance off with 1 cobalt, so that means that cobalt has the 2+ charge. And then our last one, phosphorus with oxygen, molecular compound. Phosphorus trioxide. Okay, questions on any of those? All right. You have obviously a whole bunch of naming worksheets. If it is something that is still giving you trouble, I would advise you to use them and the keys I posted last week in Google Classroom, okay, so that you make sure you are really, really consistent at doing this, because it will be impossible to do reactions well if you can't write the formulas and names of compounds. Right? So it's one of those kind of fundamental skills that you have to have in chemistry. Right? So if you're still struggling with it, make sure you're practicing it, because on Tuesday you'll have a quiz that'll be on naming and solubility most likely. Okay? So that's where we're kind of headed. Sorry, tomorrow we'll be on naming and solubility. Yeah, well, might not have solubility. We'll see. See how far we get through today. Okay. See, I was already thinking, we started talking about weekends, and I was already like, it's the weekend! But it's only Wednesday.
It's only Wednesday. See
It's
that?
that
Oh,
stupid
Wednesday,
fake
and you're
Saturday.
like, it's hump day. I'm like, no. It's still basically in the beginning.
Okay, so lesson 8 in your notes package, guys, is what you need to find here. All right, we're going to talk about solubility. Most of this terminology should be a review for you, because you talk about solubility and stuff in junior high science. I think it's like grade 8 science. Okay, so we're going to just go over some terminology that should be a review. We're going to learn how to use the solubility chart on the back of your periodic table. Okay, there's a solubility chart there. We're going to learn how to use that. Okay, and then we're going to talk about why water is the exception to basically every rule that we have in chemistry. Okay, it's a polar molecule and it does all this strange stuff. All right, so those are the key points for today. All right, so obviously we saw yesterday in our lab, not everything dissolves at the same rate. Okay, solubility is a physical property, and it varies from compound to compound. Some compounds are incredibly soluble, and some compounds are almost insoluble, okay? Meaning that they basically don't dissolve at all, like oil won't dissolve in water. Okay? So that's what solubility is, the degree to which something will dissolve in something else. Specifically, a solute will dissolve in a solvent. So there's your terminology, right? Solute is the thing that is dissolving. Solvents are the things that do the dissolving. Water is typically our solvent. That's why it's called the universal solvent, which is really a bad name because not everything is soluble in it. Okay? All right. So if I have this here on the left, okay, I've got this test tube here. I've got this obviously solution in it, okay? How do I know that this is a solution and not a mechanical mixture?
But it's one thing. You can't separate it. Like you can't tell. You can't see.
Yeah, there's no visible difference, right? It's all one homogeneous mixture, okay? And that's the term we use, homogeneous or homogeneous, however you want to say it, okay? That's one single mixture with one visible part. That means it's a solution, okay? This one here would be what we would call a heterogeneous mixture, because it has more than one visible part. Something here is not dissolving entirely or may not dissolve at all. Okay? We often refer to that as a precipitate, okay? Because typically a solid that forms will fall to the bottom like snow. Okay? So precipitation, right? So it precipitates out of the solution. It falls out of solution like precipitation falls out of the sky. All right, so if a substance is insoluble or remains insoluble in a solid form, okay, we call it a precipitate. And when we do our reactions lab in a couple of weeks, we'll have a couple of reactions that will actually form precipitates. So you'll mix two solutions, okay, with only one visible part together, and you'll get something insoluble, a solid will form, okay, and it will fall out of the solution, okay, and you'll see that precipitate form. All right, so terminology here, a solution is any mixture that contains a solute completely dissolved in a solvent. It is also known as a homogeneous mixture, all right, because the prefix homo means one, okay, one or the same, okay, is what the prefix means, right? So if you have a homogeneous mixture, then you have one visible part, okay? You often see that on food products, okay? If you buy milk, for example, milk is homogenized. It keeps the cream from separating from the rest of it, okay? When you keep it in the fridge, you don't have to shake it, okay? Peanut butter, okay? Unless you get into like super organic stuff, it is homogenized. That means that the oil doesn't separate from the rest of the peanut butter. If you get all natural peanut butter, you have to stir it every time, okay? Because the oil comes out on top. All right, a heterogeneous mixture is often also called a mechanical mixture. It is something that is being forced together but isn't actually dissolving. I can mix them together, but they're not, dissolving into each other. So oil and water would be an example of that. I could put iron filings in sand, okay, and mix them together. The iron filings don't dissolve in the sand or vice versa, okay, but they are mixed together mechanically. A mechanical mixture can be easily separated by a physical means. A homogeneous mixture cannot be easily separated unless something is boiled off. Okay, so if we boil off the solvent, most of the time it's water, then whatever was dissolved in it would remain behind. Remember that, if you're ever boiling water, don't walk away from it on the stove. Right? It'll boil away, and then all the minerals that are in water will burn onto the pan, and it stinks badly, and it'll ruin your pan. It's basically really hard to get like burnt calcium off of the bottom of the pan. Okay? I've never done that. I'm not speaking from experience in so many pans. Okay, yeah. All right, so does that make sense? Now, if I had iron filings in sand, how would I separate those two things?
Magnet.
Yeah, exactly. Stick a bar magnet in there, stir it around, and you'll be covered in iron filings, okay, and have the sand free. If you go to like a sandwich store, like Subway or something like that, they often have salt and pepper in the same shaker because it apparently saves a whole lot of time. Okay, that's a mechanical mixture, right? The pepper is not dissolved in the salt or anything; they're just mixed together, and they can shake them out at the same time. All right. Questions on solutions and mechanical mixtures and the terms homogeneous and heterogeneous? Okay, because I'll be using the terms homogeneous and heterogeneous often. Okay, that's what we typically use in high school. All right, a solute is a substance that is being dissolved. So if I put sugar in coffee, okay, the sugar is the solute, the coffee is the solvent. Okay, if I am, trying to clean, let's say, like the door to my shower, right? Then the solvent I'd be using would be water or Mr. Clean or CLR or something like that. Okay, a cleaner is often referred to as a solvent because they help us to dissolve things that are hard to get off with water alone. Right? So solvents are any substance that will dissolve another substance. How many people have ever used like oil-based paints or oil-based stain? Okay, how do you get that off your hands and off your brush? Will it come off with soap and water? Not if it's oil-based, right? Because oil won't dissolve in water. So you have to use paint thinner, bar salt, okay, gasoline and diesel fuel. I wouldn't use those. Okay, kind of, well, not that the other ones aren't flammable too, but they're a bit more flammable, so I wouldn't recommend using those. But oil-based paints will dissolve in those because they're non-polar. Okay? They're a different type of solvent, and so we can use them to dissolve things that water can't.
What about bubbly water? Would that change anything?
Bubbly water?
Yeah.
No, it's just carbonated. So all they've done is it's actually a solution where the thing dissolved is gas. So carbon dioxide is dissolved in there. And at normal atmospheric pressure, when you pop it open, it starts to come out, right? It bubbles. If you open a can of soda In a submarine, it doesn't fizz. Okay? Chris Hadfield, before he went to the International Space Station, was in this underwater research lab, and there's a video of him, and he takes a can of Coke and he shakes it like crazy. Now they're way, way down, right? So there's a lot of water pressure on top, which means there's a lot of air pressure in the habitation module. Shakes this thing, shake, 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 shake. Like it barely makes a sound, and there's no fizzing because there's so much pressure in the air that the carbon dioxide can't fizz out of the pop, out of the solution.
Oh, wow.
Yeah. Okay. So pop will actually be flatter at sea level than it will be at altitude. Okay. So if you had 2 cans of Coke or whatever, and you opened one here and you open one at sea level, less at sea level because more air pressure on top. If you open them in space, it'll be really messy. Yeah. Yeah, because there's no pressure in space, right? That's why you can't go into space without a suit. Okay? If you go out into space without a suit, all the gases that are normally dissolved in your blood, nitrogen, oxygen, all that, boil. Okay? They try to become gases because there's no pressure to keep them in there, and you pop. Okay? There's some science fiction movies that do a pretty good job of grotesquely showing what that would look like. You basically turn inside out.
Oh, that's.
Oh yeah, it's awful. It would be it's right up there on my ways I don't want to go. Like right up there with inhaling molten rock. There's like explosive decompression. They're kind of together.
Right.
What? You don't have a list of ways you don't want to go?
No, I do.
Oh, I
You haven't had enough
definitely
time
do.
to think about it.
Except mine are stupid. Like those would be like on the top of my list, whereas like falling off of like a golf cart or falling off of like a tree.
Yeah, those are like undignified ways to
Yeah.
die. They're not necessarily
Exactly.
painful, they're undignified.
Exactly.
No, I get it.
So I think it'd be cooler if everyone was like, oh my gosh, she exploded in space. That's so cool.
Well, it would mean you were in space. Not many people can say that.
Exactly.
But they'd have a hard time getting all the parts of you.
Do we know that from personal experience? Do we know that from personal experience though that you can turn inside out, or is it just like?
Well, I say
that's
turn inside out. You don't
accidental?
literally turn inside out, but you
You explode.
rupture.
Explode.
Have they seen that happen?
Yes, not to a person, but during the space race, they did experiments on animals with
Oh.
yeah,
Oh.
low pressure
Just like people
environments.
that are like, don't test on
It's pretty
animals."
nasty. And unfortunately, also quite acutely painful because you are conscious for most of it. Yeah, it's not until the pain makes you pass out that you would.
Yeah, but sometimes they keep you awake for like surgery on your foot.
Yeah, I had arthroscopy on my knee and I was awake for it.
That's.
It was really cool.
Oh.
Yeah, because they're like grinding away. They got the,
Oh.
they got that thing in the knee and they're.
No.
It's awesome.
So what
No.
happened?
It's too far.
Needed to get those
Yeah.
surgeries.
Did you see it happen? Or did I heard
Yeah.
it?
No, I was watching it on the screen. I was watching it there. Yeah, it was really cool. I asked. 'Cause I wanted. They're like, "Oh, we're gonna put you on." I want to watch.
Did they numbed it so you couldn't feel it?
Oh yeah, I had a
Yeah.
local.
Thank
Yeah,
God.
I had a local.
No.
No, I wouldn't have been joyfully watching it grind away on my knee.
I was
It's
like,
nothing.
You gotta feel it. I want to feel it.
Okay, so precipitates. Okay, precipitate's another term. Okay, that's any solid that's produced in a reaction and will not dissolve in solution. Okay, and I'll show you a quick one of that here. It's nothing like life-changing or anything like that, but
people that add like 6 packets of sugar in like a 6-ounce coffee.
okay.
I've seen it.
So-
It's funny.
Solubility, guys, the definition of solubility is the degree to which a substance will dissolve in another substance. So that's an important definition to know. Okay, how much solute can go into solution before the solvent becomes saturated. Okay, saturated is another term you need to know. If something is saturated, it can hold no more. All right, so if it's a solution, you won't get any more to dissolve. So like those people who put 6 packets of sugar in a small coffee, okay, the last swallow is really thick, okay, because they've saturated the coffee. No more sugar will actually dissolve in there, so you get this semi-solid stuff on the bottom, okay, where it's not all dissolved because it's become a saturated solution. If you drink like regular soft drinks, so Coke or Pepsi or anything like that, okay, those solutions are nearly saturated. Okay, if you've ever seen how much sugar actually goes into a single can of pop, It's quite shocking, actually. Okay? It's a lot of sugar. And try this at home sometime. Pick up a can of diet and a can of regular. A can of diet's lighter, and if you put them in water, the diet can will float, and the non-diet will sink. Okay, yeah, there's that much difference, like the sugar versus the sweetener, the artificial sweetener. Okay, so some things should be soluble, and some things shouldn't. Okay, to give you an example, the modern Twinkie. The modern Twinkie is soluble in water, which is weird because it's supposed to be cake.
Yeah.
Okay, the original Twinkie was made with real ingredients. And I'm guys, don't get the idea that I'm like one of those people that I only eat organic. I had like cheese filled Smokies and stuff last night. Okay, so I'm not preaching to you that you have to eat all natural or anything like that, because I'm totally not that guy. Okay, but the modern Twinkie is much different than its original predecessor. Okay, the original Twinkie was made with things like you would expect cake to be made out of: flour, eggs, milk, butter, okay, stuff like that. Well, the problem with that is that the original Twinkie had a shelf life of about 2 or 3 days because it was made of natural ingredients which could turn and spoil quickly. That's not good if you're Hostess, the company that makes Twinkies. In fact, they went out of business in 2013 and then were bought out and revived. Okay, but if your product can only last on the shelf for 2 days, it's got to sell fast, or you're losing a lot of money. Okay? So they started tinkering with the recipe, started replacing natural ingredients with non-natural ingredients. That, okay, like butter, like a butter replacement, an egg replacement, milk replacement. Okay, and all these things, believe it or not, are quite soluble in water. Okay, like if you've ever made hot chocolate from the powder, right? Just pour it in water. That's supposed to be milk, and like hot chocolate's supposed to be made with milk, but it's made with this stuff that dissolves in water. Okay, milk's got fat in it. It doesn't, you know, like so. The ingredients that they replaced it with, because they weren't natural, increased the shelf life. Okay, because they replaced like actual sugar and stuff with high fructose corn syrup and stuff like that, which increased the shelf life from 2 to 26 days. Then after 2013, when Hostess went out of business and then was purchased, they redid the recipe. Okay? And they replaced a few more ingredients. The shelf life of a Twinkie is now 45 days. Okay? So a Twinkie has so few natural ingredients in it that it can last for a month and a half on the shelf before it's unsellable. Okay? But that has changed it quite significantly. If you took the original Twinkie and put it in a glass of water, it would have swollen up and just absorbed all the water like a sponge, but it wouldn't dissolve. Okay, I mean that's what cake does. Well, the modern Twinkie dissolves. Really about the only thing that doesn't entirely dissolve is the filling, because there's still a little bit of shortening, vegetable shortening in it. Okay, that basically is kind of oily and doesn't dissolve. Okay, so yeah, some things are soluble, some things are not. Okay, but they've had to add a lot of stuff to this new Twinkie, because the original Twinkie was made with like things like eggs, which had certain colors. Right, the Twinkie's yellow. Everyone knows the Twinkie. It's yellow. It's yellow cake. Okay, it actually originally had banana filling. Okay, banana cream filling. Okay, so it actually tasted a lot different. They replaced the vanilla, I think it's in 1931 or something. No, it was during World War II. There was a banana shortage during World War II, and they changed it to vanilla. It was easier to get. But yeah, so the stuff that they replaced the eggs with doesn't have a yellow color. So the Twinkies came out looking like they were made of drywall paste. Okay,
You know,
like just gray. Well, nobody's gonna buy a cement-looking Twinkie off the shelf. It's not as appealing. It doesn't look natural. So, yellow dye number 5. Okay, yellow dye number 5 is a known carcinogen. Means it causes cancer. Okay, it's actually banned in most of the European Union. Okay, and I think in a few states as well. Okay, but yeah, it's in small amounts. I mean, if you're only eating, you know, 1 Twinkie a week, it's not a big deal. If you're eating 10 Twinkies a day, like you buy them by the case, you're eating a lot of yellow dye number 5. Everything in moderation, right? If your diet consists of 60% Twinkies, you should probably have a look at your diet. Okay, it's not really good for you.
Drink a little bit more water.
And a little bit more water. Yeah. And you're going to turn yellow, probably. Okay. But yeah, so they've got, you know, all these artificial ingredients. They've obviously added preservatives that increase the shelf life. Okay. A lot of those same preservatives are used in mortician's fluid.
Ew.
Yeah, that's exactly what you think it is. Okay, it's the stuff they inject into corpses to keep them presentable for funerals. Okay, so no, I'm not kidding.
That's disgusting.
Yeah. In moderation, the stuff is not bad for you.
I'm so happy
If you
I'm
have
in
10
moderation.
Twinkies a day, well, you'll be well preserved.
1 Twinkie a week, 7 Twinkies a week. It's not great for you.
Yeah,
Just
one
take
a
the
week,
Twinkie
maybe
out.
not even one a week. It's a treat, okay? It's not supposed to be a main part of your diet.
I've never had a Twinkie ever, and I'm kind of happy about it.
You've never
Yeah.
had a Twinkie?
I've never had a Twinkie.
Well, you gotta have one.
Kidding.
You gotta try.
Yeah, you haven't lived until you've had 1 Twinkie.
And one or a ding dong.
Oh, yeah.
Those are
Yeah.
even better because they're chocolate.
Yeah.
See, it's a chocolate Twinkie, but it's also got like a chocolate coating. So it's that much worse for you. That's why it tastes that much better. You can always tell how bad something is for you by how good it tastes.
Yeah.
Okay? You cook something with butter and it tastes awesome. Why? Because it's full of fat.
meat
Yeah.
is more authentic than Subway meat.
Okay,
There was a test made.
so your solubility chart. So if I get everybody to go to the back of their periodic table, I'm actually going to call up the real one here because this is different than yours. And we're going to have a look at that.
Meat is more authentic than Subway meat.
Subway tastes good.
That was definitely
This is way better than something.
good. I don't like Brazils. I don't know. Sorry, no offense. I like Brazil. Period. I know. No, I know. Oh, what are you doing?
Okay, so this is your solubility chart on the back of your periodic table. Okay, this is what can tell you whether a compound is soluble in water or not. It's very, very easy to use. Okay, what you do is you look for your non-metal, okay, whatever's acting as the non-metal in the top row, and then you go down below it. If what it's with is in the first row, then it's soluble. If it's in the second row, then it's not soluble. Okay, so it's very, very easy to use. So what I'm going to do is I'm just going to copy it over.
I'm so confused.
Okay, I'm going to demonstrate it if you're a bit confused, okay?
I appreciate that. See?
Okay, so you've got this chart, okay, on your periodic table. And so let's say I'm given this compound here, okay? Let's say, so I'm given sodium nitrate, and I'm asked, is this compound soluble in water? All right, it is soluble in water. Here's how I know. I look at my ion row, and nitrate is right here. Okay, so now I go down below. It says it's soluble, so solubility is greater than blah, blah, blah moles per liter, very soluble. Okay, it says it's soluble with most things, which is only there to save space. Okay, they should realistically list everything it's soluble with, but that would be a big, big chart or really, really tiny writing. So it just says most. Okay, so I'm like, all right, great, it could be part of most. But what I just do is I go down here and I look, all right, sodium's not down here in the second row where things are not soluble. So that means that this is
Soluble.
soluble. That's how it works. Okay? So all I have to do is look up my non-metal and see what it's with. So what about this stuff? That stuff is not soluble, right? So I look up fluorine, it's right here, says soluble with most things, but here's lithium down here in the second row where things are not soluble. Right? So lithium fluoride, not soluble in water. Okay. Everyone following how that chart works? It's pretty easy to work once you kind of see how it goes. All right, I'm going to write a couple down here, and I want you guys to tell me, okay, just write them down and write next to them soluble or not soluble. So let's go with,
I'm just here for comedic relief, guys.
I actually needed that today. My LA club.
No, I have my own LA class to go to, and then I have to hand in my homework. That's currently not in my binder. Because my friend has it. So I'll just get them to hand it in for me. No, probably not.
okay, take a quick minute and give those ones a try there.
I trust him roughly.
Would you be the trick?
Jake.
Oh,
Yeah. Oh, yeah.
Yeah. Yeah, I love it now.
that's all good. That's true.
All right, so the second one, sodium carbonate. Is that soluble or not?
Yes,
It is soluble. Here's the trick, okay? On this chart, again, to save space, they wrote group 1 ions. And you guys are probably going, okay, what's that? Okay, well, the periodic table is organized into groups. Each column is a group. Group 1 is the first column. So carbonate is soluble with anything in group 1. So that would be hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Okay? All right, so anywhere where it says group 1 ions, that just means the first column of metals on the periodic table. Right? That's why I picked that one, so that we could explain what group 1 ions are. Okay, let's quickly look at the last ones here. So I got lead 2 chloride here. Okay, so I've got to look for my non-metal. So chlorine is right here. Says it's soluble with most things, but lead with the 2+ charge is listed there as something it is not soluble with. What if it was lead 4 chloride?
It would work.
Then it would work. Okay, it didn't list lead 4. Okay, in there. Right, so it would be soluble with lead 4. All right. And then for copper 1 fluoride, okay, and important that I know this is copper 1 because it's multivalent, right? Copper 1+ is is soluble with fluorine because I don't see it here in the non-soluble row, so that would be part of most. All right, and then lastly, ammonium nitrate. Basically, all nitrates are soluble. Right? It's just these rare, weird polyatomic ions that aren't even listed on your chart, okay, that it's not soluble. So basically all nitrates are soluble. All right, tomorrow, your quiz will have naming and probably a couple questions about the solubility chart.
Oh my goodness.